Okay, so since this is machine translation, I will speak in English without any translation. Maybe next year we'll have a synchronous one. Okay, sorry. Okay, so as you probably know, neural networks have also conquered machine translation. NLP has, in the last, I would say, 3 or 4 years, completely fallen to deep learning. This happened slightly later than other fields like image or speech recognition. And it's quite interesting to consider why that was. I'm going to talk to you today about how we've been building on the advances in neural machine translation and our existing expertise in statistical phrase-based machine translation. So Yandex Translate has been around for at least 8 years. We believe it's probably the best translation system for English, Russian, Russian-English at least. And we've taken advantage of the recent research in neural machine translation and our own research, and we've coupled that together with our existing phrase-based system. And I want to explain to you in such a way that you really understand, firstly, why machine translation is the most interesting problem to work on, and also what the real advantages of neural networks are in this field, okay? So here's the outline of my talk. I'm going to give you the intuition behind the differences of a neural and a phrase-based system. So a phrase-based system is the system that was making machine translation popular on the internet since the early 2000s. And we have combined phrase-based statistical MT with the neural system to produce our hybrid system, which we launched in September. And we're building on this in many ways. So hopefully at the end of the talk, I will have a chance to explain how we're making use of the characteristics of the neural system. Okay, thanks. Making use of the characteristics of the neural system to do completely new things that we couldn't even imagine doing, really, with the phrase-based. Okay? So first, let's start by looking at some translations. It's always funny. Oh dear, it's not a very good translation. Even I know that "животное не пересечь улицу" is just not really grammatical Russian. Okay, we have a slightly better translation. One of these translations, both of these translations are from Yandex Translate. One is from a phrase-based system, and one is from a neural system, okay? You may have a guess, okay? But let's see another example. Drifted off to sleep. Drifted off to sleep is slightly idiomatic, so it means to fall asleep slowly, okay? So actually, this translation captures that information quite well, okay? Проваливалась в сон. Sounds reasonable. This translation, on the other hand, утонул, чтобы заснуть. It's kind of crazy, wow. What is this person trying to say to me? So, okay, as you can see, we have, if you go back to this example here, this example is quite broken, but you can probably still understand what the English meant, even if you didn't understand English. This one's obviously more fluent, but the previous one was completely adequate with the information. Here, we have an adequate and relatively fluent translation, but this one is fluent in the sense that it's grammatical, yeah, but it's completely crazy. It's not an adequate translation. So these two concepts are quite important for us. And why do they happen? So I hope that in about 5 minutes, you will know exactly which system produced which one in each of these examples, okay? So let's start. The key difference between the neural and the phrase-based system is the way that we represent the language. So the representation is the key thing, and out of that stems basically all of the other differences in the system. Very simply, we used to think in NLP that we didn't need to worry about how to represent our data. So we used to see our colleagues working on speech or on image, and they had to think how to convert these signals into something that was easy to process with a computer. We just thought it's easy. You take the words, you map them to arbitrary symbols, and you use these as the keys in your model, okay? So that's what's known as, let me try this. Okay, wow. Okay, maybe not. This is what's known as the one-hot encoding, and next to it is so that's the representation on the left, is the representation we would typically use in a phrase-based system. On the right is the representation we would use in a neural network. The key difference is that the neural network basically has some structure to the way that we represent the words. So I'll explain that in a bit more detail. Okay, a phrase-based system. Imagine we wanted to translate these words. He stood by the bank or on the bank. We would just simply learn a huge table of parameters. We learn this statistically. It's some kind of machine learning, but it's very simple in its representation. We just map words to words that we see in the training data, okay? We don't try to understand how to represent these words in that space, okay? It's very simple. It can memorize phrases really easily. If it's seen a phrase only one time in the training data, it's possible for it to know how to translate it. But this parameter space is very hard to work with, okay? If you want to include additional context into your parameters, you're going to have to increase the number of parameters significantly. In fact, even if you just wanted to include a single bit of information, you would in principle, need to double the number of parameters you had, okay? So it's not very efficient. The neural system, on the other hand, it maps these high-dimensional one-hot encodings into a much smaller space. Probably not 3 dimensions like here, but something a lot smaller than the whole vocabulary. And the key thing is that we make the network learn how to represent the words while it's also learning how to translate. So it's all part of an end-to-end optimization problem. The network learns both to embed words on the source side and on the target side, and it also learns how to transform the input sentence into the target sentence, okay? So, what are the results of these differences in representation? Well, in the phrase-based, because you have these discrete parameters, you basically have to break down the translation process into some discrete steps. So say you wanted to translate "he stood on the bank," you could break it down using the phrase table into some phrases, like this. Oh dear. So you get words which kind of make sense, they don't fit together, and you get this because you make lots of independence assumptions. You make independent assumptions about the phrases that you're using, okay? You get many such possible translations which are not really Russian, they're just pieces of Russian, okay? Fortunately, you can kind of make this work by using a language model. The language model also makes independence assumptions if it's an n-gram model, but the independent assumptions are orthogonal, and they can therefore choose between these different ones. So for example, the phrase "he stood" could translate to "on stoяла" if it was just the phrase table that was doing this. But a language model would tell you that this is a bad sequence, okay? So it kind of works, but it's kind of a bit clunky, okay? The neural system. The neural system just really does everything in this space of embeddings. So you have the state vector, which is maintained at each step. You encode the source word, and I'll go into more detail about this, but basically you encode each source word in your sentence. You update the state vector at each time in some way. You decode by simply finding essentially the closest embedding to the state. And in theory, in theory, there are no explicit independence assumptions. You can condition your translation on the whole input sentence and actually the prefix of the translation you've generated so far. So there's no explicit independence assumptions. So this is how it looks. You say you're translating the sentence "the hippopotamus." You you encode your words, you update your state. Let me see if I can do this again. Oops. Okay, it's a bit hard. But each of these dots is meant to be a state. So you update the state each time as you take in the new embedding. Okay, and then you start translating. You just do a maximization over your vocabulary. You choose the most likely word, which is begemot. Ciel, yedu. Okay, and it all works, kind of. The problem is that actually neural networks also are not able to model all of the statistical dependencies in the data with a finite and constant amount of space. So the word embeddings in this vanilla model, you can assume they're a fixed size. Okay, so that means as the sentence gets longer, you have to forget something. Okay, you can't possibly store more and more information into a vector of the same size. So, and actually, if you take a neural network like this neural network will not outperform a phrase-based system. It's actually do quite a bit worse, specifically on longer sentences. Fortunately, people have been working on this, and there's a couple of nice ideas. So you can learn where to depend in the source sentence. So make your network have some parameters which allow it to decide which of the source words to look at when it's translating. So the idea here is very simple. When I'm translating the first word, probably I should look towards the beginning of the sentence, in fact, to hippopotamus. Okay? And gradually like this. Okay? So it's learning, the network is learning what to pay more attention to and essentially learns the dependencies in the data. Okay. So now, the very last thing about the neural system, and this is something about the network that we actually use, which is a variant of the transformer network. Look at this word here, it. Where we are, it. It's such a simple word, but, oops, move. Okay. It's such a simple word, but it's very hard to translate. So if you look at this sentence, the hippopotamus ate the food because it was tasty. Okay? It could refer to hippopotamus or food. Okay? You probably all realize that if it's going to be tasty, it should be the food. Yeah? And that's correct. And because it's the food, we should translate the word to ana rather than on. Okay? But this is not a simple problem to solve. Yeah? And actually, the network we use here is learning not just to make dependencies between the source language and the target language, it's also learning to make dependencies within the sentence and understand when it encodes this word it, that actually it should look at the word food because of the word tasty. Okay? And that means that it's able to also know that when you change the word tasty to hungry, you should completely change the dependencies in your translation. So what I want to show you here is that the neural machine translation models that we use, they don't use any linguistic information as such. We just optimize them to solve the problem of translation. But because of the structure of the network, because the fact it's able to learn dependencies both within and across the languages, it ends up, in this case, solving another problem of NLP. This is typically called coreference. Okay, it's a problem for that people have worked on very long. So it's very interesting that we can see that the approach we take in neural machine translation is actually able to solve various other problems of NLP. Okay. Final part on this, the difference between the two systems in terms of how we optimize them. And this is quite important because it affects how we can adapt the systems. So phrase-based system is a sequence of separate optimization problems. This is simply because with the discrete space that they encode the parameters in, it's very difficult to immediately learn the whole end-to-end model. People wanted to do this. I remember when I was starting my PhD in 2003, that my advisor, he really wanted to work on end-to-end optimization for machine translation, and it just wasn't really feasible. Okay? So what you do is you take your corpus of translations, you align the words, because that's one problem you can solve somewhat. You then extract phrases, which is this phrase table, and then you optimize the phrase table as one of the features in a linear model. So at this point, the very last, oops, where are we? You can possibly incorporate some other metrics. But basically, there's a lot of different optimization problems, and it's quite difficult to incorporate, say, some feedback from users or something. Exactly. So it's difficult to add side information to the optimization problem. Neural networks, as we all know, one of the main reasons people like using them is that they are able to, you can optimize them end to end. We just simply optimize the log likelihood of the data. Okay? It's quite easy if you can encode some additional information that you have into the state vector, and I'll give you some examples in a minute. It's very easy to use that information to somehow influence the translation. Okay? It's also possible to add additional terms to the loss in a way that will be accounted for, not optimally maybe, but globally. Okay, so phrase-based, very simple, can memorize things, but doesn't have very fluent translations. Okay, so it's adequate. It can convey the information. It may not sound beautiful, but it can convey the information. The neural models, on the other hand, they really take into account all of the context and everything that's being fed into them, but because they have to learn how to represent words in the space, they need to see some examples. You can't learn what the relationship is between hippopotamus and hippopotami, the plural, without seeing those words quite a few times, okay? So they have lots of problems they have lots of problems when translating words they haven't seen very frequently. Okay? So, which system produced this? The phrase-based? Yeah? Yeah, phrase-based. That's true. And this one, obviously, is the neural network. Yeah? And this example, drifted off to sleep. This is actually the phrase-based translation. So here, the phrase-based really is better because it's just memorized it. It didn't have to do very much. The neural network is so busy trying to make a fluent, well-structured sentence, it does something completely crazy. And now it's worth thinking about what's the difference between working on machine translation, say, in academia or in a company like Yandex, where we have a public service which is used by millions of people every day. One of the big differences is that you don't just care about the average quality of your translations, you also care quite a bit about the variance and about the outliers. So if we have very crazy translations sometimes, it will really affect user confidence very much. Users use Yandex Translate very often because they don't understand something or because they're trying to write something in a language they don't speak so well. If they see us producing crazy translations, they will be less likely to continue using us. And even if the translations aren't perfect, it's preferable to avoid really crazy errors for that reason. Okay? So what did we do? We used Cat Boost. So we have a classifier, we train it to predict the difference in quality between our phrase-based system and our neural system, and we choose the best translation. It's an extremely simple ensemble, okay? This is how it works. Can I have a banana? We translate it with both systems. We do this online. Я могу есть банан. You understand what it means, but it's not very good Russian. Можно банан. Okay, so Cat Boost chooses the right one. And drifted off to sleep. And these are real examples from the system. Our neural system is not allowed to produce that. We realize that there that really isn't a good translation, and pick the phrase-based one. And the interesting thing to remember here is that the cat boost, where are we? Cat boost? is using lots of features that we have from the phrase-based system. So the phrase-based system, it may produce unfluent translations, but it has lots and lots of information which it's memorized, which we can use in this classifier to actually help choose between the systems. Okay, so that was a little the part about the two different systems. What are we doing now? So we launched the hybrid system in September last year. There's a lot of things I didn't talk about here. Our team is here. They will answer your questions about the different engineering challenges we had. We were the first product, I believe, in Yandex to use GPUs for user traffic. And that was quite a challenge. Okay? But what have we been doing since then? We've been doing lots of things because actually, although the quality has jumped significantly with neural machine translation, I believe there's still a lot more gains to be had within this paradigm. And that, at least for a couple of years, I hope we see a lot of growth. And I'm going to present a couple of the things that we're working on right now. So, okay, so one other thing we did, and actually this is a bit of an aside. This is to do with the Yandex, our approach to making sure that we have the best translations for our users every day. We know that actually our users translate lots of the same things. So what I'm showing here is that it's a bit hard to see, but about 10,000 queries, unique queries, explain about 30% of our traffic. So if we can translate those 10,000 queries really well, we will please at least 30% of our users. Okay, it's really quite good. We also have these things called dictionaries, and these dictionaries are all built semi-automatically. So we have a lot of machine learning, a big pipeline which learns the different definitions. We identify words which users are using on Yandex Search and which we're not able currently to translate. We try to find translations, and we also use the Yandex crowdsourcing platform to get additional translations. So anybody know what Lifterlook is? Yeah, what is it? Exactly, yeah. And Yandex would be able to tell you that. So this was something we launched just a couple of months ago. But what I'm showing you is that we have these dictionaries, which are not just some static dictionaries. They're updated all the time, and they cover many of the most popular translations. So we use these dictionaries to polish the top 30% of the traffic, and thereby we really can improve the perceived quality, the actual quality for the users, not just some average that might be, yeah. Okay, how about maybe the more exciting things? Well, we can encode additional information into the NMT system if we have it. Okay, we might have some information about the user, we might have some information about the context where they're doing the translation. Maybe they're doing the translation on Yandex Browser. So Yandex Browser, you can automatically translate the whole page. It's one of our big clients. It could be somebody's translating Yandex Mail, it could be anything. But if we take the example of Yandex Browser, if you had the word in English, can you see this? If you had the word home, okay? So home, it's an easy word. Doma, okay. Главное, okay? So this is actually about to be launched. This is a beta. I just did some screenshots a couple of days ago. What we have here is we have the English of the Financial Times website. We have our previous translation, which it's okay, but it's not adapted to this specific context of web page translation. And what we did is we used information from the page, we said, we know from the HTML that this is a navigational tag. This is navigational text, or this is a title, or this is content. And based on that information, we tuned our model. And therefore, we learned some nice domain-specific translations. So Glavnaya is probably a better translation in this context. Okay? And just to give you some idea how we did this, on this graph, on this axis, this is the quality. This is quality measured by an automatic metric, but it's a reasonably good approximation. The quality on the y-axis is for the general domain. The quality on the x-axis is for this specific domain. And what we did is we fine-tuned our existing model using this domain-specific data. If we just did that sort of naively, then we do get improvements, because it goes to the right, but it goes down on the general domain. What we were able to do is we were able to incorporate a term which penalized the model for differing too much from the baseline predictions. So in other words, we have a Kullback-Leibler divergence. It's the divergence between the distributions of the predictions of the model before it was tuned and after it was tuned. And by incorporating that term in the loss, which is this is really simple to do, you are able to get better translations on the new domain and not lose any quality on the general domain. Okay. So future directions. Future directions, I think we are a big search company. We have a lot of data, and we're starting to use more and more of it for translation, but actually we still have a lot more to use. We have started to use context, but we have so much more that we could do there. There's so much more information. For example, when you're translating on Yandex Translate, maybe your previous translations give us some idea about what you're actually trying to do. Maybe you're trying to write a letter to somebody. Maybe you're trying to do your homework. Maybe this information is important for us helping you get the best translation. And obviously, the way that we currently integrate the phrase-based and the neural system, it's very, very simple. There are much more sophisticated ways to integrate the two, and we're experimenting with quite a few of those. So, and there's also some interesting problems. So this is a problem we're collaborating with the research team on. So, Vasya готовится к соревнованию по плаванию. Он плавает очень хорошо. Okay, it's such nice Russian. And the English, Vasya is preparing for the swimming competition. It floats well. This is, I don't believe any public machine translation system at the moment actually solves this problem. But we have a solution for this. And we have many other problems like this, which are really important to solve. And there's just so many different things we're working on right now. Okay? Finally, a happy graph, just to give you some idea how much progress we've been making in the last, actually just 6 months. And this is purely the changes we made using data. So in the machine translation community, there is a big evaluation every year. It's called WMT. They have different data sets each year. So we have the last 3 years. The blue column is one of our competitors, and the pink column is when we launched the hybrid system in September, and as you can see, we've launched 2 times since then, at least 2 data launches, and the quality is going up significantly, so it's quite an exciting time. Okay, so thanks. I'll leave you there.
Thanks, David. Поскольку Дэвид, он сам гораздо лучше, чем любая машинная система перевода, то вы вопросы можете задавать на любом языке, и он вам ответит.
Hello.
Hi.
Let's talk a bit more about data.
Yeah.
So, as I understand, you use parallel data.
We do,
it's very carefully prepared data. That is, you need 2 sentences, and you can just put the text and its translation, like a big chunk of text, like a book, you need really to spit out the individual sentences.
That's true, yeah.
So how do you see improvements along these lines? Maybe use some semi-supervision where you just, as I said, throw two parallel texts, big texts, or maybe even use something like unsupervised NMT. There was a paper recently.
Okay, so that's a really interesting question. The first thing to say, our data pipeline it has some supervision in it in terms of we have some labeled documents which we can evaluate our data mining against. But basically, it's an unsupervised process. So we try to mine millions, if not billions, of documents from the internet. And then once we've got a pair of documents that we are convinced are probably translations, we try to align the sentences. And we apply various classifiers and filters to make sure at the end we get quite clean data. Okay, so yeah, the problem of building we have a team that works a lot of the time on building the data for us. That's how important it is. Okay. The second question about unsupervised, yes. We will definitely be exploring unsupervised machine translation more. We've done some experiments internally. We will definitely need to do that. We have, in the past, had these projects for minority languages, low-resource languages spoken in the Russian Federation. And for those languages, there's very little data. And although we were able to build phrase-based systems, it's going to be a really hard problem to do that for neural machine translation. So we will definitely at some point have to look at unsupervised for those languages. We have some students actually working on a project related to that right now. Yeah. Thanks.
My name is Roman. Thank you for your...
Thanks.
And actually, my question was about unsupervised learning too,
Okay.
but I will ask it again.
Sure.
Is it possible to retrieve the sense, the meaning of the word lift a look using unparalleled corpuses, for example?
I mean, there are definitely techniques that people have used to learn translations of words without using any parallel data. So, for example, you might expect the word liftaluk to occur in similar contexts to the English phrase elevator selfie. Okay? Of course, it's a very noisy problem, but yeah, there's definitely a lot of different approaches that try to use that fact that, you know, liftaluk and elevator selfie, they refer to the same phenomenon in the world, so they should be associated with roughly the same phenomenon. So you might find the word, we had the expression glamourny liftaluk and trendy elevator selfie. You might, if you already know that glamourny and trendy are translations, it could help you with the context. Yeah.
Спасибо за доклад. Меня зовут Арсений. Возможно, вы знаете, скорее всего, что Google несколько лет назад запустили так называемое сообщество переводчиков, когда они всех желающих просили переводить и отправлять им тексты, переведенные с одного языка на другой. Использует ли Яндекс такие сообщества, или если нет, то планирует ли их создавать?
Okay, so that's a good question. So, sorry, I'm going to answer in English, but I think you're referring to the Google Translate community, yeah? Yeah. So, we have feedback, we use feedback, we've definitely, I mean, the examples here is, some of this is from, where are we? The dictionaries. The dictionaries make use of the feedback that we get every day from the Yandex Translate website. So to that extent, yes, we do use user feedback. We definitely want to do more of that. We're also working on projects with professional translators to try to get feedback from them, because we think that's an interesting area that hasn't really been tapped yet. But yeah, it's clear that without using user feedback, we're missing out on a lot of useful information.
Hello, thank you.
I'm sorry, I move on to add some
Yeah,
more
sure.
details.
Yeah.
I mean that Google creates a challenge.
I see what you mean. Yeah, they actually create a sort of they give users an incentive to submit this information. We should definitely look at that kind of thing. Yeah, we should. I'm not sure how successful that is in Google. I know that for very popular translations, they seem to be able to use that data, but I'm not completely aware. They haven't published any work that shows that it has a huge impact. So yeah.
Hello, thank you for this information. I have one question. You use embeddings and you use two very difficult languages like English and Russian. And a lot of regions speak on Russian and a lot of regions speak in English. And in different regions, people use the same words in different contexts.
Yeah.
And different contexts have different words. So we have big variance in embeddings. How do you deal with this?
Are you talking about the problem where the same word could be used with different meanings in the same language? Yeah.
Yes. No,
Exactly.
example, car in English it may be lift cabin and car machine, and in Russia lift is lift and machine is machine.
Okay.
And the second is, if you know, in St. Petersburg we have porебрик, and in Moscow we have bordure. So we have two different worlds, and when you do embedding, you have very close points.
Okay.
And
so I won't do a demo now, but I can give an example. I think this is related to your question. So, if you have the name in an English sentence, Andrew, it seems like a simple name. If, for some reason, you realize that this person is actually Russian, it could be that the correct Russian translation is Andrei. If, on the other hand, you can see that this person is American, then probably the correct Russian translation is Andrew. Yeah? So this is the kind of ambiguity that you have everywhere in language, even where you don't see it. Yeah? This example, I think it's quite clear that we can solve it a lot of the times using the self-attention. So if you have a chance to try out Yandex Translate and you come up with different sentences, if there is information which allows the translator to distinguish between these two possibilities, there's a good chance that we will get it right. If there's no information, then of course we just have to produce the most probable one. Okay, but that's, yeah. So we hope we can fix this. Maybe in some point we will use the location, the geolocation of the user to help improve the translations. It's not impossible. I don't think it's actually even that far away, probably.
So right now you don't add any additional metadata to words.
No.
Only embedding.
No. We just only the embeddings, and we've just started adding metadata from the browser to do contextual translation there. But it's the same techniques could be used to do user adaptation, and we definitely want to do that. It's really important. Yeah, thanks.
Hello, my name is Dmitry, and my question is about the ambiguity which can be in every sentence, even if we don't see it.
Yeah.
The classical example is, I saw a man on the hill with a telescope, which actually means have 5 different meanings. How do you handle with such ambiguity? Can you even detect it, or you just take any average translation you get by your system? Thank you.
Okay, so I would say that if you looked into the mind of the neural network, which is these networks, where are we? Let me just go back. This thing here, yeah? So what I'm trying to show with this diagram is that the connection that the network makes between different words is stronger or weaker depending on the sense of the translation. Okay, you probably would find that there are some connections in our model which correspond to or similar to the dependencies that you see in a syntactic parse tree. Okay, so your problem with the man with the telescope. You saw the man with the telescope. Did you see? Is it depending on the verb or is it depending on the noun? And I think you probably would be able to use our network to solve these problems. I don't know for sure, but I wouldn't be surprised if it learns some of these things. And it learns that, for example, the word saw and the word telescope, well, telescope is something you see with, so it's probably connected as an instrument. Okay. Oh. But I mean, yeah, of course there could be more than one translation.
The problem with this sentence is that even human isn't able to distinguish these 5 different translations.
But maybe,
do you see them?
I see the problem, but I think that in the context, on its own, yeah, it's true, it's an ambiguous sentence. But if you said, I've lost my telescope, and somebody says, I can see a man with a telescope, then it's not ambiguous at all. Yeah? So in reality, language is usually not ambiguous, otherwise people would be very confused. So I think we need to use context just like that. Yeah.
Yes, David?
Yeah.
Hi. Thank you very much.
Thanks.
So the question is, why did you choose the blue metric for your classificator? Because, well, I want to explain to everyone else here that it doesn't correlate with the human assessment and evaluations. Mm-hmm. And, for example, the prompt system where I work.
Yes. You're right.
It has always been the best system in English Russian until last year, according to human evaluation. But according to Blue, it was always in the lower part, lower cluster. Yes.
No, I think you're completely right that when you compare systems that are completely different, and particularly when you compare a system that has more manual rules. I mean, there's a very old paper, well, very old. It's 2010 maybe, or maybe a bit older, 2006 maybe, from Callison Birch and Miles Osborne. Miles was my advisor, but they were always making these experiments and how blue is not good, and particularly when you compare human perception with blue, and one of the systems is a manual one, because a manual one might not produce the most fluent ones, but it almost always gets things right, often gets things right, and humans often prefer that. Here, it made sense for us to use blue because we were using 2 different statistical systems. Okay? And although the results I presented here were comparing our system with one of our competitors as well, we also run human evaluations. Human evaluations are just much more costly, so we don't run them quite so often. But we do human evaluations, comparing ourselves with different competitors. Yeah.
So it's not related to resources. So if you wanted to, you could use human evaluation.
We do use human evaluation.
And don't you think that statistical and neural are so different that blue isn't really good for it? So your research says it's okay.
Well, we've mostly compared our hybrid system with third-party neural systems. And our hybrid system is actually about 80% neural. So we feel that comparison is okay. But you've got a good point. Yeah, this is something that we're looking at in the classifier which we use to choose between this, where are we? God. So here, the point is, I think your main point here is that we shouldn't be using blue to optimize this classifier. And yeah, possibly we could do better. But we definitely think that it works reasonably well right now, and it improves on not using the classifier in terms of reducing stupid translations and actually improving quality slightly. Okay.
First of all, thank you for your report.
Thanks.
And my question is, we all see that methods works well for English, maybe Romanian languages, but what about, for example, Korean or Chinese?
Yeah, good. Well, okay, so firstly, Korean and Chinese, really, really different.
Yes.
So actually, Chinese phrase base worked very, very well because there's not very much morphology, so there's not much agreement. So you can put these independent phrases together, and it's not as bad as it might be. Korean, just like Japanese, very, very different word order and quite a lot of morphology. We have seen really big increases in performance going from phrase-based to neural for these particular languages. So Japanese, Korean, Turkish as well. Turkish is a very similar structure to Korean and Japanese. And that's probably because the sentence structures are so different, you kind of need to see the whole sentence in order to translate. And so the phrase-based system, which breaks it into pieces, it can't see the whole sense of the input sentence. Particularly when you translate from Korean or Japanese into English, I would imagine the neural system to be much better. Okay, so.
What about Arabic?
Well, Arabic, I don't know, but I would imagine that the results are somewhat similar to Russian. So it's got a lot of morphology, so probably the English-Arabic translations have become more fluent. Okay. So, I mean, for Russian, it's really very clear. You can just, even I can just see that there's a lot fewer errors in the agreement.
Okay, what about word base or corpuses for that languages? Because for English and French, there's big and huge word corpuses, but for some, for example, for Hindi, there's very little.
There's a lot of people who speak Hindi, but probably, yeah, you're right. There's not so much. It's probably not as much as for Russian by a long way. I mean, at one extreme, we're going to have to do something unsupervised. Okay, so. And maybe for languages in the middle, like Hindi, where there's quite a lot of data, but maybe not as much as we want, we will need to look at ways to share data from other languages. So Hindi is an Indo-European language. Maybe we can use all of the European languages and Indo-European languages together and train a model that way. That's definitely been tested in some settings. So
thank you.
Yeah.
Здравствуйте, спасибо за доклад.
Спасибо.
What kind of features are you using as the cat boost inputs?
So the features are quite simple. They're related to the length of the translations. There's some features related to the characteristics of the stupid translations we see. So, for example, repeated words, missing words. We use a lot of features from the phrase-based system, so the phrase table. The phrase table is just a big dictionary of phrases in English and Russian in this case, and we can use that to assess translation. We also use a language model, but they're pretty basic features. It's actually a very simple classifier. Yeah. Yeah.
Hello.
Hi.
My name is Dmitry. As you said, there is a lot of NLP problems, and while solving translation problem, transformer solves syntactic tree building problem.
Possibly, yeah.
So,
yeah.
Have you researched what if we force our network to solve other problems too, and do kind of transfer learning from this? Does it really help?
Okay, I haven't personally, and I don't think we have in our team, but there's a very interesting paper by Kevin Knight from last year or the year before, where he basically takes the encoder from an NMT system, and he uses the encodings to try to, as features, to predict dependencies in a syntactic parse tree. And what he shows is that, particularly when the languages are very different and you have to really understand the syntax of the input sentence to translate, the encoder is able to produce really useful features for solving this completely separate problem. Apparently separate, but actually it learns it. So yeah, I think what you're suggesting is a good idea. The only possible drawback is that there's not much data for these other NLP tasks, because what is amazing about translation is there's billions of translations on the internet available for free to learn from. Okay, they're not billions of parse trees. There's only the ones that have been made by linguists, and they take a long time, and they're quite small. But yeah, but it's a great idea.
Thank you.
Последний вопрос, после чего у нас будет целый перерыв, где можно будет всех любителей перевода задавать.
Hi. Thanks for the talk.
Oh, hi there.
So I have a question about your anaphora coreference resolution.
Yeah.
So actually what you have is an anaphora resolution. So you have
Yeah,
a solution for anaphora.
Yeah.
But what about actual coreference? So what I mean is, like the sentence, not the hippopotamus ate the food because it was tasty, but the hippopotamus ate the food because the animal was tasty. Do these words, like the animal, behave the same as pronouns, or?
I don't honestly know, but I can guess that they might not, because. No, the reason that it's just a complete guess, but my reason for that would be that it's not possible to translate the word "it" without resolving this possible. Yeah. So in other words, when it's being trained, when the network is trained, it sees the word "it" and it sees the word "ana." Yeah. So it's trained to basically see these associations. Yeah. On the other hand, if it sees the word "animal," it might, I'm not convinced that it would need any information from the other words in order to correctly translate that, and therefore it might not learn that. So it might be an effect we see just for pronouns, or maybe we see it more for pronouns. But we should definitely look into that. That's true. I mean, I can just tell you for that last, this thing here. This is definitely solved using some kind of attention, okay? The same kind of mechanism. It's in different sentences, but using the same kind of attention.
Okay, thanks.
Thanks.
Большое спасибо.